Yeah, good afternoon, students. It's my pleasure to introduce this new topic on resolution techniques, part 2. So, in the previous classroom discussion topic, we had a discussion on two important techniques used for resolving these collisions, like linear probing and quadratic probing. We discussed. Now, in today's classroom discussion topic, we would like to discuss remaining two different methods, like double hashing and rehashing techniques we are going to discuss in this particular session. So now I would like to share my screen. Hope my screen is visible to you. Yes. So this is week 13 lecture 2 resolution techniques part 2 that we are going to discuss. Fine. So summary of the previous CDT is that we had a discussion on the collisions resolution techniques, open addressing and separate chaining. These are the two popular methods. The open addressing is also known it as the closed hashing, and this chaining method is called it as a open hashing method. So under this open addressing technique or closed hashing, we discussed about linear probing and quadratic probing in the previous session. Now we would like to discuss about double hashing and rehashing. We would like to discuss in this particular session. So the learning objectives of today's session is that we would like to discuss about the collision resolution techniques, double hashing and rehashing techniques. The lecture outcome is that after completion of this session, students are able to solve the problems on collision resolution techniques using double hashing and rehashing methods and able to compare and analyze these four important collision resolution techniques like linear probing, quadratic probing, double hashing and rehashing techniques. So collision resolution technique. So double hashing. So double hashing uses one hash function and then repeated steps forward and interval until an empty location is reached. So the interval is decided using another separate independent hash function to resolve that particular collision. So hence the name double hashing. So in double hashing, we are using two hash functions rather than a single hash function. So first hash function is used to identify the location in the hash table. If the location is already occupied, then we will say that collision is occurred. Then we are going to use another hash function to resolve that particular collision to find the location in the hash table to store that particular value. Fine. So the hash function in case of double hashing, so we can define that hash function as h of k comma I is equal to h dash k plus I into h2 of k. So where mod m, where m is the size of the hash table and h1 of k and h2 of k are the two hash functions. H1 of k is equal to k mod m and h2 of k is equal to k mod m prime. So where the I indicates the probe number varying from 0 to m minus 1 and m dash is chosen to be less than m. So generally m dash is chosen as m dash is equal to m minus 1 or m minus 2. Fine. So when we have to insert a key capital K into the hash table, we first probe the location given by the following hash function h1 of k mod m, because during the first probe I equal to 0. If the location is vacant, the key is inserted into it, else subsequent probes generate locations that are at an offset of h2 of k mod m prime from the previous location. So let us take an example. Consider a hash table of size 10 using double hashing technique. Insert the keys 72, 27, 36, etc. into the hash table, and you can take h1 of k is equal to k mod 10 and h2 of k equal to k mod 8. These are the two hash functions you can take to insert these keys into the hash table. So let us consider this m is equal to 10, size of the hash table. So initially the hash table is taken from 0 to 9 locations and all are empty, so we will store minus 1 into it. So we have h of k comma I is equal to h1 of k plus I into h2 of k mod m. So this is a hash function we are using in double hashing. So h of k comma I is equal to h1 of k plus I into h2 of k mod m. So if you want to insert the key 72 into the hash table, so we will substitute I equal to 0 and k equal to 72 into this hash function 72 mod 10 plus I into 72 mod 8 and then mod 10. So 2 plus 0 into 0 mod 10 2. So T of 2 is vacant. So 72 is stored in the second location. Similarly, 27 is mapped to the seventh index location. So seventh index is also empty. It will be inserted into this seventh index location. So like that, 36 is mapped to the sixth location. Sixth location is also empty. 36 inserted here. So like this, 24 is inserted into the fourth location without any collision. So 63 is also now mapped to the third location. Third location is already empty. So without any collision, 63 is inserted. So 81, key 81 is mapped to the index location 1. 1 is also empty. So we will insert 81 into the 1 location. Fine. So next 92 is mapped to the second location. So already T2 is occupied. So we cannot store 92 into the second location. Therefore, we will try for the next thus substituting the probe number I equal to 1 at this time. So 92 is mapped to this index location. Okay, so sixth index location it is mapped here. So sixth index location is also occupied here. So we will substitute I equal to 2, probe I equal to 2 for storing of this 92. Then it is if you substitute h of 92 comma 2, so we are going to get it as 0. So t of 0 is also empty. T of 0 is now empty. So we will insert 92 into the 0 location. So similarly, k is equal to 101. So 101, if you try to insert that, it is mapped to first location. First location is already filled. So we got this collision. So probe I is equal to 1, we will substitute. So when I equal to 1, if you substitute, it is now mapping to sixth location. So sixth location is already occupied. So we have to substitute I equal to 2. Then repetitively, if you apply this process to insert this key 101 into the hash table, although double hashing is very efficient algorithm, it always requires m to be a prime number. So in our case, m is equal to 10, which is not a prime number, hence the degradation in the performance. So had m been equal to 11, the algorithm would have worked very efficiently. Thus, we can say that the performance of the technique is sensitive to the value of m, which is nothing but size of the hash table in double hashing. Fine. So this is another technique which we are going to discuss, which is called it as a rehashing. So when the hash table becomes nearly full, so the number of collisions increases, thereby degrading the performance of this hashing technique. Like insertion and search operations, time complexity is increased. So in such cases, a better option is to create a new hash table with the size double of the original hash table. So all the entries in the original hash table will then have to be moved or mapped to the new hash table. So this is done by taking each entry, computing its new hash value and then inserting it into the new hash table. So though rehashing seems to be simple process, it is quite expensive and must therefore not to be done frequently because it requires additional memory is required here and recomputation of the new hash function to map already mm, existing keys in the old hash table to this new hash table. Fine, that is what we are saying here. So this is an example for rehashing. Consider the hash table of size 5 given below. The hash function used here is h of x is equal to x mod 5. So rehash the entries into a new hash table because already this hash table is filled with 4 entries. So now that new hash table is of double the size of this because 10 locations we have to take double the size of the original hash table. Now rehash the key values from the old hash table into the new one using the hash function h of x is equal to x mod 10. So we will map these values into this new hash table. So this is what we are calling it as a rehashing technique. So now this is the reflection spot. So what are the different types of collision resolution techniques discussed in this CDT? So if you are not able to answer this, please watch the video from the beginning. So lecture outcomes are revisited here. After completion of the session, students will be able to solve the different problems using collision resolution techniques like double hashing and rehashing methods, and also compare all these four different types of open addressing techniques like linear probing, quadratic probing, double hashing, and rehashing methods. Summary of this session is that we discussed in this particular session these two important collision resolution techniques which will come under open addressing. So that is double hashing and rehashing are the two important techniques we discussed. That in double hashing we will use two different hash functions. We will use that. Okay. So one hash function is used for mapping and other hash function is used for resolving that collisions. So when the hash table becomes nearly full, the number of collisions increases, thereby degrading the performance of this insertion and search operations in the hash. So in such cases, a better option is to create a new hash table with the size double of the original hash table, and then all the entries in the original hash table will then have to be moved to the new hash table. This is what we are calling it as a double hashing. Fine. So this is a lecture level practice problem. So you have to solve this considering the hash table size is equal to 11. So apply the double hashing techniques to insert the following keys into the hash table by considering these hash values. Fine. So these are further readings on this particular topic. So thank you one and all.